If you, like me, are interested in science-related content, you most likely know Veritasium channel. Some time ago they made a great video about rainbows that got me thinking if I could replicate this optical phenomenon using a ray tracing program I wrote a while ago. I won't go into details today, but I did everything needed for a realistic rainbow rendering. It had the proper refractions and even was using Fresnel equations for internal reflections. To test this, I recreated the experiment from the video. Here I have a screen with a hole in it for sunlight to shine through. It then should hit the droplet and project a sharp circle on the wall. However, something goes wrong here. The circle is not sharp at all. I checked the code and it turned out that the internal reflections weren't quite right, so I had to flip the normal in this case. Now, with this problem fixed, we have to implement light dispersion. After a quick search, I found a Wikipedia article on Zelmar equation. It is essentially an approximation for the dispersion. Here we have coefficients for some kind of glass. At the bottom of the page I found a link to this website that actually had the formula for a wide variety of materials. What we need is water. Here's its refraction index, and below the graph there is the formula. All I need to do is to put it into Excel to calculate the indexes. So now I have 31 different wavelengths and the respective refraction indexes. This covers the entire spectrum and should hopefully give better results than just the red, green and blue light. In the shader I make an array with the indexes and get the needed value from the ray's wavelengths. It also defines the color of the ray, which I simply take from a gradient I found on the internet. Let's try running the code. Now you can clearly see the colored ring. It looks better when I turn down the brightness and look at it closer. After some optimization, including making a better screen that now only lets the direct sunlight pass through, I was able to make a little better picture. Well, normal rainbows are cool, but with the ability to simulate them, I wanna try something different. What if the rainbow appeared on a planet with two suns? What if by some miracle it rained on Tatooine? Adding a second sun is as easy as writing a couple more lines of code. As you might have expected, we now have two rainbows. The red sun gives a monochromatic rainbow since it only has the red light. So let's change it to yellow. Now you can clearly see the red and the green. And here are cyan, magenta and yellow rainbows. If you've played Death Stranding, you've seen the weird upside down rainbows there. As I was looking through the screenshots of it, I stumbled across this photo and a tweet that said it was real but was not produced by rain. The first comment even said what it was called. And indeed, circumzenithal arc is a real thing produced by hexagonal prism-shaped ice crystals. Now I wanted to code this as well. So I looked up the parameters for ice on the website. It's for ice at 150 Kelvin, which is kinda cold, but I don't think it's a big deal. I again put the formula in the same spreadsheet and copied the new indexes into the shader. On a website that really helped me to code the shaders, I looked for intersection functions. And luckily there was a function for a hexagonal prism. So I just copied it and changed a little for it to fit into my program. The prism looks good on the outside, but the reason I render it in the debug mode with the normals shown is that the internal intersections might not be right. And sure enough, this looks completely wrong. Good thing that I've already solved this issue for boxes earlier, so I just added the rotation and did the same thing to fix the problem. And now everything looks right. So I just turn off the debug view and see the rainbow, right? Well, at this point I realized that my method of rendering was awful. Let me explain why. So I have a rough screen, a sun, a droplet and a camera. The camera shoots rays at the screen and they get scattered in all directions. Some of them hit the droplet, get refracted, reflected and then hit the sun. But most of them just miss it completely. So how do we force all of them to pass through the sphere? This would greatly improve both the speed and the quality of the image. I tried to deal with this when I optimized the code by adding a bias to the reflected rays direction. Then more rays would hit the sphere. And it kinda worked, but there's another issue. Currently, the rays from the sun to the droplet are perpendicular to the plane, so it isn't that noticeable, but for an upside down rainbow, it must come at an angle, which changes the projection on the plane. Now that the cone comes at an angle, we wouldn't see a circle, but an ellipse. How do we avoid this? In the real world, there are millions of little droplets the light passes through, so all the spheres together form the picture. But we can't afford to simulate such a big number of objects. It would be too much, even if I bother to optimize my code. But we can do it the smart way. Let's shoot the ray first and then move the droplet so that we guarantee it will be hit. Then we do the same thing for another ray, and another. See, now by moving just one sphere, we have the same effect as if there were millions of them. Now if we do this with a bunch of randomly rotated horizontal hexagonal prisms, we hopefully will see an upside down rainbow. Here's my implementation of this idea. In the ray structure, we store not only the ray-related attributes, but also the parameters of the prism. In the intersection function, we take those parameters instead of the hard-coded ones. And as we shoot the ray, we move and rotate the prism. Let's see what we get. No way it actually worked on the first try. I didn't even speed up the footage like before. The new method allows the picture to be rendered almost instantly. We can also see the other lights appear in the sky. These are called sundogs, and they form at the same time as the circumzenithal arc does. We've done the upside down rainbow and the sundogs, but a full sun halo has other parts, and naturally I wanted to replicate them as well. It should be easy to do just by rotating the prism around the other axis. I quickly coded just that and hopefully we should get a gorgeous halo. That doesn't look right. Maybe I'm rotating it around the wrong axis? Let's try again. That's a bit closer, but still off. Now it has a weird loop in the center. And now it's just the sandog. I was clearly doing something wrong here, so I had to Google this again. Here's a paper that has some pictures and a lot of text. Yeah, I ain't reading all that. Let's look at another one. It also has some diagrams and even more text. Nah, I don't wanna read any papers. I need a working program I can copy. What's that? Halo ray. It is exactly what I'm looking for. There is a link to GitHub, but I don't wanna try to understand someone's code. So I just download the program. This is what the program looks like. I hit the render button and the halo shows up. I can change the position of the sun, the field of view. I can also turn the light scattering down so that we can see the halo clearly. But most importantly, we have the crystal settings. By changing the angle, I got those weird halos I showed earlier. This is it. I just had to figure out the angle. But I didn't really understand what was going on until I hit that minus button. A part of the halo just suddenly disappeared. I hit it again and now I saw the same thing I coded the first time. So it turns out that there are 3 types of crystals. The plates that can be represented by this case for weights for my mouse don't fall sideways like that, but rather horizontally. It's the aerodynamics that causes the body to have the maximum air resistance while falling. So it can only rotate in one plane and won't wobble that much. The second type is columns. They are just like a pencil. They do not fall vertically as their air resistance is at max when they lie on their side, so they rotate around 2 axes. Finally, there's this shape that has its height roughly equal to its diameter. Its air resistance is pretty much the same in any orientation, so it ends up just randomly rotated. Actually, Veritasium already made a video about snowflakes that described all these types and had this diagram that showed under what conditions they form. To recreate this, I made an array of 3 prisms and added a population parameter to the array which determines what prism to draw. Then it takes the right prism, changes its shape, position and orientation, and applies all of the changes. So, let's build the halo. We start with the plates, then we add the columns, and finally the randomly oriented crystals. Here's the result compared to the halo array program, and to a real photo. Lastly, as a little bonus, I wanted to try making a rainbow using diamonds. After all, they are all shiny, so this should look good, right? I repeated the process and made an octahedron crystal, since it seems to be the natural diamond shape. The diamond looks nice, so I'll render a rainbow with it. And the results do look interesting. I especially like this halo. But those wouldn't appear in nature, even if it rained diamonds. The octahedrons would most likely be orientated randomly, which only makes the regular circle rainbow, except way smaller, because of the higher refraction index. So I think it was a fun little experiment, and I mean both the video and the project. It is my first full-length video with editing and a voiceover, so I hope you liked it. If you did, let me know by clicking the like button. I do not promise to make similar videos in the future, because I will make anything I like, really. It can be a DIY project, it can be a travel blog, it can be a cooking video, whatever. But if you wanna watch this type of content, where you never know what comes next, then you can also subscribe to this channel. That's it for today, and thanks for watching.